So this was the presentation I gave to Mine Excellence Conference back in mid-March in Santiago about reducing water, energy and emissions through great engineering. And to begin with, I'd like to share some of the trends in the Australian mining industry. So since 2000, the Australian mining industry has doubled production. But over the same period, water, energy and emissions have more than doubled, such that today it takes 28% more water, 21% more energy, and 16% greater emissions to generate a unit of product compared to back to 2000. This has been linked to a decline in the resource quality of material that's being mined, and the declining productivity, increasing water, energy and emission intensity of production is not unique to Australian mining. This has been seen in a number of studies around the world. The chart there shows the actual and projected copper head grade decline since the year 2000. And over the coming periods, there's going to be an increased demand for mineral resources, increasing the amount that's produced from a declining resource quality requires much greater productivity. So there's a new challenge airing for the mining industry. In terms of energy productivity, back in 2007, the US Department of Energy released a benchmarking report, which benchmarked the energy efficiency of mining and mineral processing equipment all around the world. And what they identified was there could potentially be a 17% reduction in energy usage at metalliferous mining operations today, just by adopting the most energy efficient equipment that's currently available. In Australia, the Energy Efficiency Opportunities Program in 2010 introduced mandatory reporting of energy saving opportunities for Australia's high energy unit using industries. Not only did they have to report the magnitude of the energy savings, they also had to provide a business case for the adoption of that saving. They didn't have to do it, but they needed to provide it. This resulted in the focus being on easily implementable opportunities, the low-hanging fruits at operations, and only resulted in a 3.2% reduction in energy usage at metalliferous mining operations. In terms of water productivity, largest water usage at the sites typically in mineral processing and leaching. Largest water losses occurring in tailings disposal through evaporation, entrainment and seepage. One possible technology is that of high density tailings disposal, so thickening up the paste of the tailings before throwing it out to the tailings dam. And this can be supported by high rate, high performance thickeners, encouraging greater water recovery and reuse in mineral processing. It has potential water savings of about greater than 30% at some sites. Great engineering is another technique or process that could help with the energy emissions and water intensity of metal production. So great engineering, as we all know, applies coarse separation techniques to remove uneconomic material from ore, recover economic material from waste, or exchange high value and low value material between different processing destinations. And this is done to enhance the quality of ore being processed, improve material allocation decisions, and increase the value of the asset over its life. It also results in reducing energy emissions and water intensity of metal production. So some of the core separation techniques that we look at here at CRC Ore include separation by screening, sensing and sorting, and gravity. And these different levers, they require different attributes of the rock ore focused on different scales of grade heterogeneity or differences in specific gravity of ore and waste for the separation technique. In terms of this paper, the scope was to evaluate and compare the value proposition and production impacts of energy efficiency by deploying the most energy efficient equipment currently available water efficiency, looking at deploying high-density tailings disposal, and grade engineering, looking at coarse separation techniques to improve the quality of ore being processed. It was a retrospective evaluation of the case study site, and the key metrics were looking at changes in the net present value of the operation, changes in total production, and changes in water, energy, and emission intensity of that production. The methodology that was applied derived the optimum cut-off grade policy for the deposit. This defines the allocation of material over each period over the life of the mine. And it was based on a modified version of Lane's theory to incorporate pre-concentration techniques. The next stage is, once we have the optimum cut-off grade policy, we can then quantify the amount of material that's being mined, treated as ore, and the product that is going to the refinery, and the amount of metal that's being produced. So we can use these numbers to start to quantify what water, energy, and emissions intensity of production would be like on an annual period over the life of the mine. And this is used to construct the annual cash flows and the value of the operation as well. We can then compare each of the different scenarios to the base case to work out what the change in the value and the water, energy, emissions intensity of production is for each scenario. It's a holistic approach. It covers every period over the life of the mine, and it also covers every activity in the value chain across mining, processing, and refining. The case site was a low-grade open-pit gold-copper porphyry deposit in Australia. It was in operation between 1999 and 2013. And water was supplied to the site from catchment, site balls, tailings return, and waste effluent from a local town. The site processed 17 million tonnes of ore at an average water consumption of 0.9 kilolitres per tonne. Total water requirements at site amounting to 15.3 gigalitres per annum at a budgeted cost of about $3.1 million per annum. The electricity requirements to pump that water around site amounted to 1.5 gigawatts per annum, and at a budgeted cost of about $100,000. The energy and emissions from the site, there were three main energy sources considered in this valuation: the electricity that the site used, the diesel fuel that the site used in mobile mining equipment, and the AFO explosive from the site in the mining process. The electricity was 426 gigawatt hours per annum at a budgeted cost of $22.3 million per annum. 13.4 million litres of diesel fuel, $3.6 million per annum. 12.5 kilotons of AFO explosive at about $9.8 million per annum. The energy associated emissions amounted to 417,000 tonnes of carbon dioxide equivalent per annum, and 92% of those emissions were due to electricity consumption from a coal-fired power station. So the charts at the bottom there break down the energy and the emissions by activity across the value chain. And what we see is the largest use of energy is in the crushing and grinding, and accounting for about just over 50% of total energy use. But the same processes use electricity predominantly, and they account for over 2/3 of the emissions that were released in the mining process.
Is that the, sorry, Mike, is that the equivalent emission from the coal-fired power station?
Yes.
That it consumes?
So it includes Scope 1 and Scope 2 emissions. So Scope 1 is everything released at site,
right, and
Scope 2 is from the consumption of electricity. So the energy costs at the site were relatively cheap. The diesel price, 27 cents per litre. That was after a diesel fuel rebate was returned to the company. It's still quite cheap by today's standards. The energy, despite the energy being cheap, total energy consumption accounted for over 1/3 of the total operating costs for the operation. The first scenario I looked at was one of water efficiency, looking at high density tailings disposal, reducing water losses of about 280 litres per tonne of tailings, which was about a 31% reduction in total water consumption from the site. There was an increase in electricity company for pumping the paste instead of tailings, but this was partially offset by a reduction in energy consumption for sourcing additional water. The capital expenditure was estimated at $5 million to upgrade pumping facilities. The second scenario was one of deploying the most energy efficient equipment currently available. The estimated energy savings were taken from the US Department of Energy's report in 2007 and ranged from about 10% to 33%, 37% across the different operations at the site. This amounted to a net energy reduction of about 19% per annum for a capital expenditure cost of about $20 million, which represented a 5% increase on equipment capex.
Mike, before you go on, what's some of the savings that they had within some of those categories? Like, was it just changing out some of the pumps and flotation? Or?
Yes, so what they looked at was the best performing sites and the equipment that they employ. So it's not only the equipment, it's also I guess the operational excellence of the site as well. So they call it best practice, and this was used as the benchmark to go. All the sites performed at this benchmark, and this was what each activity would be reduced by.
Some big numbers.
Yes. Can you make any comment on that 23% energy saving lasting?
It's been a while since I've looked at the report. I'm not sure what that is. That could relate to rock properties as well in the past. So I can't give you too much there. The report itself is quite generic. So it's looked at a number of operations and just gone, you're the best of the lot. That's what can be set forward as the benchmark.
It'd be interesting to see with the sites with the lowest lasting costs lined up with the sites which have lowest grinding costs.
So taking the costs away, I mean, this was just on the energy basis. So if there was a site that was in soft material, then it would be sent as the benchmark. If there, again, I mean, some of the loading and haulage, if there was a site that didn't have to haul particularly far because or had very favourable conditions, it would be sent as benchmark. The third scenario was looking at grade engineering, so looking at screening to exploit a natural deportment of grade to finer size fractions. Copper and gold at the site were assumed to deport with equal responses, and screening could recover 75% of the metal in the finest 40% of the mass. 2 mobile screening plants were deployed to the mining face and powered by 2 portable diesel fuel generators, and 2 front-end loaders, also diesel fueled, were deployed to rehandle and load trucks with screened material. Total capital expenditure for the grade engineering scenario equipment costs were estimated at $17 million. The model that was used to evaluate the scenarios takes material from the block model, assesses whether or not it should go through a grade engineering pathway, where the upgraded material would go to the processing plant, downgraded material either to a stockpile or waste storage facility, or sending the material directly to one of those destinations to begin with. The energy usage around the site was quite different across the mobile mining equipment and the processing plant and refining stages, but all incorporated within the modelling. The results from the case study are depicted here in terms of the change relative to the base case for each of the metrics across net present value, production, total ore treated, the average grade of that ore, water intensity, energy intensity, and emission intensity. And by intensity, I mean the amount of water, energy, and emissions that are required to produce a unit of refined metal. If we look at the water efficiency, we see very little change in value, production, or the ore treated or grade, but quite a significant change in the water intensity of that production, reflecting a relatively low case for the low cost for water at the site as well. Energy efficiency, again, we start to see a little bit of an improvement in net present value, but not much in production. Some significant changes in energy and emissions, but none in water, and overall not a strong value proposition, but a positive value proposition.
That assumes, I mean, that's at current pricing, right?
That's at the pricing and the assumption. So the energy is cheap.
Over time, that'll go up though, won't it? The cost of those things. So you'd expect the NPV to.
Yeah. So this is these findings are not true of all sites. They're just true of this scenario. And then when we look at grade engineering, we start to see some big changes in production and net present value. We see a reduction of 23% of the ore that's going to be ground up and at the processing plant and treated. But we do see an increase of 26% in grade. Overall, there's slightly less metal, but at a more accelerated rate, which is improving the net present value. The water intensity, energy intensity, and emissions intensity of the grade engineering scenario are also reduced. And then finally, if we combine all those scenarios together, we start to see some truly transformational changes in water, energy, and emissions, and very similar productivity and value proposition being driven from the grade engineering case.
And if you added in the, if you could somehow value drop in water intensity and energy from in terms of social impact and that sort of thing, you'd add it in, wouldn't you?
Yeah, you can definitely strengthen the business case through that. So the water and energy efficiency returned a small increase in value despite significant reductions in water, energy, and emission intensity. This reflected the relatively low cost of these inputs into production. The business case, as Clyde just mentioned, can be strengthened by acknowledging the risk reductions in the energy and water supply at the operation and improvements to social license to operate. The operation itself did actually run out of water at one stage in its life and was forced to stop production, which would have been a cost that they would not have foreseen.
Did you build that into the model?
No, this was based on their long-term mine planning information, what they assumed from DADOT to be feasible.
Would the water stage be sufficient to avoid that shutdown?
It's a good question. Possibly not, but they would have had to source less water, which they were trucking in on a daily, hourly basis. The grade engineering significantly increased the value and reduced water, energy, and emission intensity of production. It did this by removing uneconomic material prior to costly water and energy intensive stages of processing, replaced that material with high value component of ore that was previously sent to stockpiles, and accelerated the rate at which metal was recovered. This reduced the total ore process and the tailings generated over the life of the mine. So combining the grade engineering and energy efficiency, water efficiency scenarios increased value and unlocked some truly dramatic reductions in water, energy, emission intensity of production. So finally, in summary, the water, energy, and emission intensity of the mining industry is increasing. Valuation and comparison of the production impacts for the case study site across the scenarios examined in water efficiency, energy efficiency, and grade engineering were performed in this paper. The focus on water and energy efficiency can significantly reduce water, energy, and emission intensity of production. It yielded comparatively low financial returns for the operation, but could be strengthened by acknowledging those risks to supply and the social license to operate at the site. Greater emphasis on improving the quality of ore being processed with great engineering can significantly increase value and reduce water, energy, and emission intensity of production. Does this by accelerating production, increasing grade, reducing total ore process, and the total tailings generated. Combining great engineering with water and energy efficiency can dramatically reduce the water, energy, and emission intensity of production and increase value. And that brings me to the end of the presentation.